This is a video lecture for Math 283, and the topic today is surfaces in space, and this is found in section 12.6 of the textbook. So what's the motivation for this? Well, we've already encountered a few simple surfaces in space, the most recent being a plane. But what we're going to do in this section is develop a more comprehensive list of surfaces, of simple surfaces we might encounter in free space. And we're also going to learn how to graph these surfaces. Graphing can be a challenge by hand for 3D surfaces, and so we're going to use an online 3D grapher to help us make these graphs. What I'm going to do is go through a set of examples, and we'll develop sort of a catalog or a repertoire of surfaces that we might encounter. So the first example is this surface here, x squared plus y squared equals 9. We're going to consider this in 3D. Now in 2 dimensions, everyone knows this is a circle. But in 3 dimensions, it has a different shape, or a related shape. Here we have no z specified, and so z can really assume any value. And what we're going to do is look at what this surface looks like as it intersects with planes z equals k. So as we look at planes parallel to the xy plane, right? This is just going to trace out a circle. And so what we get here is we get a stack of circles. And I'm going to draw this one by hand because it's fairly easy. It's fairly straightforward. Z, Y, X. We can draw a circle here, and then we basically stack these circles up, right? And these circles are all centered on the z-axis. So what we get here is a cylinder, and the radius is 3 of the cylinder. And it extends infinitely up and down along the z-axis. Now I want to talk about something called a trace. Traces will be very helpful to us in creating 3D graphs. A trace is the intersection of a surface with a plane. That's the definition of a trace. And we can now use this to define a cylinder. A cylinder is a surface whose traces are the same for all planes parallel to some plane. Or to some given plane. So basically, if we look at, in this case, if we look at x, excuse me, I labeled this z, this should be x. If we look at the xy planes here, if we look at planes, if we were given an xy plane, the trace of this surface, the intersection of this surface with all planes parallel to the x, all planes parallel to the xy plane, right, is the same. Okay, so this would be an example of a cylinder. Now let's consider another example of a surface we might encounter. How about z equals y squared? Okay, this surface doesn't involve an x. Okay, so the fact it doesn't involve an x actually tells us immediately that this is also a cylinder. Because what this means is traces of the intersection of this surface with planes that are perpendicular to the x-axis, or in other words, with planes that are parallel to the yz plane. So traces in planes parallel to the yz plane will all be the same for this surface. So this is also a cylinder, but it's not going to necessarily look like what you might think would be a cylinder. So just keep in mind the definition of a cylinder here is a little bit broader than what we conventionally think of as a cylinder. And why don't I create a graph of this in 3 space? But before I do that, we can see that if we look at what the trace of this is in the yz plane, the trace of this will simply be a parabola. Okay, so we're going to trace a parabola. It's going to look like in the yz plane, y, x, and z. This will simply trace a parabola. So we'll have a parabola, and these parabolas will be stacked up like this, going along the x-axis, creating a cylinder by the definition of the cylinder. I'm going to turn the camera around here and you guys can see what the graph of this looks like. So here we go. And let's do z equals y. Here, let me type this in. Y squared is the best way I can think of to represent this. Here we go. I can see that picture there, what you guys are seeing. So what this looks like is what it is a parabola that is a set of parabolas that are all stacked up along the x-axis. And this is cool. You can kind of rotate and see different angles there. And make sure that this camera is getting the full screen there again. Okay, so this is a bit of a challenging lecture to present to you guys, bouncing between the computer and the camera and the whiteboard. Let's talk about a more general definition of a quadratic surface. So what is meant by a quadratic surface? Okay, a quadratic surface is a surface that is basically can be written as a second degree polynomial in x and y and z. Okay, and it has this form, so let me write this out for you guys. ax squared plus by squared plus cz squared plus d times xy plus e times yz plus f times xz plus g times x. So you have h times y plus j. I'm forgetting my alphabet. This is a strange video. We'll go with, I think they use a j here for z, and then we do a k here, and this equals 0. So this is a mouthful, but basically this is a quadratic surface. It's a second degree polynomial in x, y, and z, and this creates a graph. You can create a graph of this. And often what we can do is we can complete the square to write these in a simpler form. Let's consider some other examples of quadratic surfaces. So I think we're on example 3. And so let's do this guy. X minus 1 squared plus y minus 2 squared plus z minus 3 squared equals 9. Okay, so does anyone know what this is? Well, this is obviously a sphere in 3 space. Its center has a center of 1, 2, and 3, and it has a radius of 3. Okay, so this is another type of surface we might encounter. We've actually already encountered this. Let's see if we can create a graph of this. I'm going to go ahead and do that. So we get x minus 1 squared plus y minus 2 squared plus z minus 3 squared equals 9. That's kind of a cool, okay, they're just showing a snippet of that. Here, I'll show you guys this. Okay, so this is actually just getting a part of our sphere. But I think you guys can see that that's, if you were to extend the range here and the domain, we would get more of the sphere. But anyway, that's a sphere. Okay, let me make sure this camera is centered. Okay, let's consider some other examples. And let's do example 4 here. So this is the example we'll consider. X squared over 1 plus y squared over 4 plus z squared over 9. This all equals 1. So the way we can get a handle as we go on here on what these surfaces are is we want to create traces. And we can create traces in the various coordinate planes. So the first trace is, let's do the YZ plane. This is the plane for which x equals 0. So what we do is we plug in x equals 0, and we get y squared over 4 plus z squared over 9 equals 1. Well, what is this? This is an ellipse. This is an ellipse. So the trace of this surface in the YZ plane is an ellipse. And then we can do other planes like the XZ plane. This is the plane for which y is equal to 0. We get this. X squared over 1 plus z squared over 9 equals 1. This is also an ellipse. And furthermore, if we do the xy plane, this comes out to x squared over 1 plus y squared over 4 equals 1. And this is also an ellipse. Okay, so the traces in the three coordinate planes are ellipses, and what this creates for us is this is actually an ellipsoid. And it kind of looks like a football. Let's create a graph of this, and I can show you guys what this looks like in 3D. So we'll do x squared divided by 1 plus y squared divided by 4 plus z squared divided by 9 equals 1. Okay, that's cool. So this is what I get. Here, I'll show you guys what this looks like. So this is an ellipsoid, and we can look at different angles of that. And it looks kind of like it's an oblong. It's an ellipse, traces of an ellipse in all three coordinate planes. Gives us an object like that. So this is another example of a quadratic surface. Okay, let's make sure this is centered. Okay. Let's consider a few more examples here. I'll go to example 5. Okay, example 5, let's consider this shape. So again, we're just creating a catalog of shapes of different types of quadratic surfaces, at least we might encounter. There's surfaces beyond quadratic surfaces. Again, what we do here is let's create a trace in various planes. So let's create a trace in the xz plane. Okay, that's for the plane for which y equals 0. We get z equals x squared. If we do a trace in the yz plane, we get z equals y squared. Okay, and then if we were to do a trace in the plane z equals k, we actually would get circles. Okay, now these are parabolas. These are parabolas. So in these coordinate planes, we're getting parabolas along the yz plane. So for example, let me try to draw this in 3 space. Then I'll create a graph for you guys. This is x, y, and z. So in the yz plane, we get a parabola like this. But we'd also get a parabola like this in the xz plane. And then we'll get circles like that. So this creates what's called a paraboloid. Paraboloid. And let's create a graph of this. So here we go. I'll show you guys what this looks like. Let's see, x squared plus y squared equals z. Okay, we're at 14 minutes. I may do one more shape and then do the rest with you guys in class. This is a paraboloid. Okay, that's what it looks like. Parabolas in the xz plane and the yz plane, and then circles in planes parallel to the xy plane. Excuse me, I wasn't showing you that, I guess. There you go. Different orientations there. Okay. Let's come back and do one more example. Like I said, I'll do a couple more examples tomorrow in class. Why don't we do this example? This is closely related to this example. What if we change one of the coefficients here? what if we have x squared plus 2y squared equals z? So now if we do traces in the xz plane, right, we get z equals x squared, which we had before. If we do traces in the yz plane, we get z equals 2y squared. And so what we're getting parabolas, but now the parabolas have different steepnesses. So there's going to be some sort of asymmetry in the way this looks. And if we do a trace in the plane z equals k, right? If we do that trace, we get x squared plus 2y squared equals k. Well, this is an ellipse. And so this shape is called an elliptic paraboloid. An elliptic paraboloid. Let's create a graph of this shape. So let me just change this equation I have. Just put a 2 in. And I don't know if you get, okay, that does show it. So I will show you guys this. This is our graph. And you can see that this is a bit oblong paraboloid in the sense that it's thinner in this direction. It's thinner in going along the y-axis than it is going along the x-axis because the coefficients are different. Okay, can you guys see that? That's fatter, that's thinner. Okay, I'm going to talk about a couple more shapes, including an elliptical cone and hyperbolic paraboloid, and there's hyperbolas in 1 and 2 sheets as well. So I'll talk about those examples in class tomorrow. This video has gone on long enough, but hopefully it's given you guys an introduction to some simple 3D shapes.